Financial Modeling, Topic 9, Bonds, Section 5. We're going to compute the VaR, or the value at risk of a bond, using duration and convexity. We've said that using duration and convexity to estimate the value change of a bond, the dV, delta V, is the duration, actually the minus duration, times change in yield plus 1/2 convexity times change in yield squared times the V. So again, minus the duration times change in yield plus 1/2 change in yield squared times convexity times initial bond value. That is the duration estimated price and the convexity adjustment. Now we're going to calculate the VaR using this formula. Remember, VaR is a delta V concept. It tells you how much money you could lose given some time interval and confidence interval. So what we're going to do is we're going to use this formula. I'm going to switch this sign here to get rid of it. And that's because we're only looking at losses. Bonds all have positive durations. So the situation in which you lose is when interest rates are up. So what I'm going to, and the VaR is always quoted as a negative, as a positive number. So I'm just going to drop off the negative sign for the minus duration and just say that the bond VaR is the duration times change in yield plus 1/2 change in yield squared times convexity times the initial bond value. However, I'm going to replace the delta Y, not with some arbitrary 50, 100 basis point change. I'm going to use a change that assumes a normal distribution. I'm going to get a change that's consistent with my confidence interval. In other words, if I'm looking for a 99% confidence interval VaR, I'm going to find a 2.33 standard deviation change in yields over that time period. So I'm going to take the Z of X, that's the 233 or 1.65 for the 95% confidence interval. I'm going to multiply times the daily standard deviation and multiply that times the square root of t to ensure that it has the proper time interval. So I'm going to just go to my spreadsheet. And what we see here is, again, the negatives are offsetting each other because I'm going to quote the VaR as a positive number. And what we see here is I have, say, the last 30-day yield of this bond. I calculated the changes in yields. I then calculated the daily standard deviation of rate changes. So there's 5 basis points per day standard deviation. I then calculate my Z of X, norm S inverse of Z. I'm going to do a 95% confidence interval, 5-day VaR. I'll calculate my delta Y that's associated with 5 days and 95% confidence interval by taking my daily standard deviation times Z times the square root of 5. So it looks like you are 95% confident you will not have a 17 basis point change in rates. However, there's a 5% chance you will have a 5% adverse change in rates, which in this case is an increase in rates because durations will be positive. And then I'll calculate my VaR. Again, we could take out these two negative signs and say that it's simply the duration times change in yield plus 1/2 convexity times change in yield squared times the initial bond value of 1103. So that number is 1985. So you're 95% confident that losses will not exceed $19.85 over 5 days. However, there's a 5% chance, assuming normal distributions of yield changes, there's a 5% chance that we could lose $19.85 or more. Sometimes VaRs are calculated as a percentage. So I take 1985 divided by 1103. My percent VaR is 1.8%. So there is a 5% chance of losing 1.8% or more. Another way of thinking about that is there's a 5% chance of having more than a 17.4 basis point increase in rates given the historical standard deviation and assuming normal distributions. So in this topic, we simply calculated the VaR of a bond